All right, in this we're continuing on page 6 from the previous problem. We're still dealing with the quadratic function that we started in the last problem, which is negative x squared plus 6x plus 3. This time it asks us to identify the average rate of change from 6.2 to 7. I've already plotted the point 6.2. Excel, when I input that in, tells me that the y value is 1.76 when x is 6.2. I also find the y value when x is 7, and I see the points down here, 7, negative 4. When I find the average rate of change, I'm finding the slope of this secant line between those 2 points. Secant line, a point that intersects at 2 places on the function, secant line. When we find the average rate of change, we're finding the slope of the secant line. So we're going to find f of 7 minus f of 6.2 divided by 7 minus 6.2. We can pop that in Excel in one calculation. I do y2 minus y1 in parentheses divided by x2 minus x1 in parentheses. So it comes out to negative 7.2. So the slope of the secant line is negative 7.2. On average, the function's going over 1, down 7.2 between those 2 points. In part F and G, we are trying to find the instantaneous rate of change of the function at 6.2. To do that, we are going to start at x equals 6.2 and travel to a point that is very, very near x equals 6.2. So in the first one, I selected 6.20001, which is just a tiny bit to the right. When I find the slope of the secant line between those 2 points, it's going to be very, very close to the slope of the tangent line, which is what we're seeking. So 6.2 over to 6.20001. So in Excel, I already have x is 6.2. Now I'm going to put in x is 6.20001. And we see that it tells us the slope of that secant line is negative 6.40001. The average rate of change is negative 6.40001. Now it says go from 6.2 to a point just to the left of it. So here's 6.2, 6.1999999 would be just to the left of it, and the slope of that secant line would be very, very close to the slope of the tangent line at 6.2. So I go into Excel, I'm going to plug in 6.1999999, and it tells me that the slope of the secant line is negative 6.399999872. We see that both of them are very, very close to negative 6.4. And in fact, I feel pretty confident saying that if we could find the tangent line right at 6.2, that right at that instant, the slope of that tangent line would be negative 6.4. So in other words, here is 6.2, comma 1.76. If we could draw a line tangent to the graph right at x equals 6.2, a tangent line, it only intersects the function at that one point. It's parallel right at that point. That tangent line would have a slope of negative 6.4. In other words, the instantaneous rate of change when x is 6.2 is negative 6.4. Example 4. Example 4, we've been given this third degree polynomial function where we plug in the number of years since 1870 and it outputs the population of Park City, Utah at that time. In part A, it asks us to use Excel to find a good estimate of the instantaneous rate of change at t equals 59. Later, it's going to ask us to find the instantaneous rate of change or estimate it when t is 88. So what I'm going to do is just have Excel find an estimate of the instantaneous rate of change at all of these points in my table, and then we can answer the question for any t value we select. Instantaneous rate of change, we remember we estimated it using average rates of change. So I want to have Excel output for me the estimate for the instantaneous rate of change here, and also here, and also here. So to do that, no matter what x value you're at, right? We want to be able to say, all right, here is a t value. Just go a little tiny bit to the right and find the average rate of change, and that will be a very good estimate of the instantaneous rate of change at that point. So I'm going to start at any t and go over to t plus 0.000001. It's a tiny bit to the right, and I'll find the average rate of change between those two. So in other words, I'm going to do f of, or s of in this case, s of t plus 0.000001 minus just s of t all over the t plus 0.000001 minus the t. Change in y over change in x. So right now I have this input-output table. I have the t's and the s of t's. I need to also have these t plus 0.000001s and s of t plus 0.000001s. So I'm going to insert those. So I'm going to insert here t plus 0.000001. Okay, so that means take the x value and add 0.000001 to it. So equals the x value plus 0.000001. I'm going to drag that down. Here we go. I want to make your column wider after you do that because these numbers get pretty large. And then I want this to be the function value, the y value. Y value at t equals 0.000001. That is s of t plus 0.000001. Okay, so I need to go back to this third degree polynomial function that we were given right here, this equation. And instead of plugging in these t values in A, I need to plug in t plus those. So I need to plug in the column C values, these values. All right, so it will equal 0.0491 times this value in column C to the third minus 6.0931 times the column C value squared plus 155.87 times this column C value plus 3784. And now I drag the formula down. All right, so once you've done this in Excel, just a quick check you can do. Your y values should be pretty similar to the original y values, right? Because these points are supposed to be very, very close together. So for example, if I go down here to row 15, the original x was 13. It should be the case that in column C, the x value is just a tiny bit different from that. And it is. It's 13.000001. And the y value original was 4,888. And this new y value is also about 4,888. They're very, very close. These 2 points on the graph are very, very close to each other. So if you go through all this in Excel and they're wildly different, you know you messed something up. You better go back and fix it. So at least do that check. Okay, now I'm going to do the average rate of change calculation. Let me make my window a little bigger for you to see. So here we go, average rate of change. All right, so average rate of change is change in y over change in x. So it will equal, in parentheses, this second y minus this first y divided by, in parentheses, this second x minus this first x. And I drag it down, make my column bigger. All right, there they are. These are the average rates of change. So from t equals 0 to t equals 0.000001, the average rate of change is 155.869937. It's very, very close. This value is very, very close to the instantaneous rate of change at t equals 0 because these points are so close together. It's a great estimate for the instantaneous rate of change. So now that we've filled in that table for the entire set of x's from 0 to 100, I should be able to quickly answer these questions over here on the page. So it asks us here, first of all, in part A, estimate the instantaneous rate of change when t is 59. So I'm going to go down here to t equals 59 in my table. There it is. So it's negative 50.3645, I'll just say. So negative 50.3649 approximately. I rounded there, obviously. So that average rate of change value in our table is a good estimate on the instantaneous rate of change at t equals 59. Interpret that value. So that value, negative 50.3649, is a rate of change. It's a fraction, change in y over change in x, right? In this case, we don't have y's and x's, we have s's and t's. So it's change in s of t divided by change in t. The numerator is people, population, and the denominator is years. So we're saying 59 years after 1870. So if you take 1870 and you add 59 to it, you're going to get 1929. So in 1929, so right at that time, right at that moment, right at that year, the population of Park City, Utah was decreasing by 50 people a year. Notice it's decreasing because that instantaneous rate of change is negative. It's saying over 1, down 50, over 1, down 50. It's saying you go over a year, down 50 people. Show how it can be seen on the graph. So we're talking about t is 59. So you see on this graph that's about here. So the x value is 59. We see on our Excel table the y value is 1854 approximately. So in that year, in 1929, there were 1,854 people in Park City, Utah. And what it means to find the instantaneous rate of change is to find the slope of this tangent line. And we know the slope of this tangent line is about negative 50.3649, going down by about 50 people a year at that time. Right, similarly, this last one says, now use Excel to find a good estimate of the instantaneous rate of change when t is 88. So I'm just going to go down in my table to t is 88. There it is. T is 88. Population of Park City, Utah was 3,776 people. And I see over here in column E, it's going up at a rate of 224 people a year, approximately. So it's about, again, this is just an estimate that we're getting. I'm going to say 224.2. Again, it's a people per year rate. And we're talking about 1988 here. So if you take 1870 and add 88 to it, you get 1958. So in 1958, the population of Park City, Utah was increasing by 224 people a year. All right, and lastly in part F, it says show that on a graph. What does it mean? So 88 says that that's a population of 3,775 people. That on my Excel file, the y value. Again, if you draw a tangent line, the slope of that tangent line is the 224.2. It's saying right at that moment in time, the population is going up at 224 people a year.